So my name is Bryce Cannon, and I'm an applied physics student here at NJIT, a PhD student, and I'm here to talk about what space weather is. To outline my talk, we'll define space weather. We'll talk about what is happening on the sun that affects space weather. We'll talk about how this space weather can affect us, why it's important to our society. We'll talk about what protection our society has from space weather. We'll talk about the forecasts that we can make to predict space weather. And we'll talk about NJIT and our research here. So, the sun is very far from Earth, 150 million kilometers away from Earth. Here is a picture of a storm on the sun. Do you think a solar flare like this could affect our society, even though it is very, very far away? Short answer is yes, and it's called space weather. Space weather is defined as activity on the sun and in near Earth space that can affect our technological material and society. So here at NJIT, the T stands for technology. We're pretty concerned about our technological material, and space weather can be important to us. So that's what it is. Let's watch a video of this storm. It's from September 10th, 2017. It was observed by a satellite called the Solar Dynamics Observatory, which is owned by NASA. So here we see this bright point of light, this solar flare. And because of the location of this flare, we can see it coming from the side. We have a pretty good view of it. Now you might have noticed some static just then. That's caused by particles hitting the instrument, the Solar Dynamics Observatory, coming from this storm. If you missed it, I'll replay that section. Just watch. There's the static. Right? So, do you guys think outer space is actually completely empty? No, it's actually not. The sun is spewing out a constant stream of particles known as the solar wind. So it's always spewing out these particles shown in yellow in this illustration, and they're kind of blowing. So you're probably more familiar with terrestrial wind, the wind on Earth. So we're going to try and compare solar wind and terrestrial wind. And this solar wind is going to be our first kind of solar activity that we're going to learn about. And we'll learn about more solar activities later. So the Earth's atmosphere typically has 2.5 times 10 to the 19 atoms in a cubic centimeter. What would you guess the density of the solar wind is? If you're guessing something a lot less, that's good. It's about 4 atoms or so per cubic centimeter, typically, coming from the solar wind. So much, much less dense than Earth's wind. The fastest terrestrial winds are about 400 kilometers per hour. How fast do you think the solar wind is? The top speed of the solar wind is about 2.7 times 10 to the 6 kilometers per hour. So that's about 4 orders of magnitude faster. In other units, it's 750 kilometers per second. Very, very fast. And what is the atmosphere, the wind on Earth composed of? It's composed mostly of uncharged molecules, nitrogen molecules, oxygen molecules. What would you guess the solar wind is composed of? So the solar wind is actually charged. It's made of charged particles like protons and electrons. So we've basically learned that solar wind is a relatively constant stream of particles. What other solar activities do we care about? So pictured here is a solar flare. This bright point of light in the middle of the sun is a solar flare. These don't last for a long time, maybe a day or so. So they are temporary points of bright light. So solar flares are made of light from the sun. Solar wind has particles. Solar wind is constant, blowing every day. Solar flares are temporary storms. What else do we care about? We care about something called the coronal mass ejection, a CME. So it's called that because the coronal refers to the layer of the atmosphere called the corona, which is the outermost atmosphere of the sun and the hottest layer of the sun's atmosphere. So some of the mass of particles in the corona is being ejected. So here, this white blob is a CME, a coronal mass ejection. And it started here and it came away from the sun. It's being ejected out. How are they related to the other types of solar activity? CMEs can cause gusts in the solar wind. They can cause the solar wind to be much stronger for a while. How are they related to solar flares? Sometimes they happen at the same time, same place as solar flares. Sometimes they don't. So sometimes there's a cloud of particles and a bright light. Sometimes there's just a cloud of particles coming away from the sun. Now, are these important? I don't know. They're billions of tons of matter at millions of kilometers per hour. That's kind of concerning. If we had a CME that's very large and directed at Earth, that could do a lot of damage. But what sorts of damage? How can it affect our society? So it's not going to affect like human health of people on Earth. It's not going to bombard our skin and hurt us like that. But if you were an astronaut, then it could directly sort of hurt you because the atmosphere, the astronauts do not have the atmosphere to protect them. It can really damage satellites. So the solar wind can bombard the electronical equipment of these satellites and make them break. It can affect our communications. It can affect how well radio waves can travel from a radio antenna to a receiver. Because radio waves, in order to go very far, they need to be able to bounce off of the upper atmosphere, the ionosphere. They need to be able to bounce off the ionosphere and come back down. And if there's enough solar wind, it can break the ionosphere, and the radio communications will not be able to go as far. So that can be a problem for planes who need to be able to talk with radio to ground control and other planes. It can affect GPS because GPS uses satellites, and we already talked about how it can break satellites. And it can affect the electrical grid. The transformers on the electrical grid can be fried by the strong currents in the wires coming from space weather. A couple of more lighthearted effects. It has an effect on the northern lights. So this is where the northern lights come from, the aurora borealis. It comes from particles of the sun coming from the solar wind, bombarding the atmosphere and giving it energy, and that energy is then released as different colors of light. And that can also affect honing pigeons, actually. There's groups of people who own honing pigeons, and they actually race their honing pigeons with each other. And they need to pay attention to space weather, because if there's a bad enough storm, the honing pigeons actually get lost and they can't find their way back home. So they use the magnetic fields of Earth in order to navigate. They don't use the sun. We know they don't use the sun because they can find their way home at night, and they can find their way home when it's cloudy. And they can't find their way home very well when there's a large space weather event. So people who race these pigeons actually have to pay attention to the space weather. Which is pretty funny. So now we know how space weather can affect us, but how can we protect ourselves, and what protections do we already have? So the first layer of protection is the Earth's magnetic fields. that's going to redirect most of the wind around Earth. So in this picture, the magnetic field is shown in blue, and the solar wind is shown in orange, and the magnetic field acts like a shield, and it's going to redirect most of the wind around Earth and past Earth. Some will be able to come around back and come back in towards the nighttime side of the Earth, but most of it's going to be redirected. So the little bit that does get towards Earth, what's the next layer of protection? That would be the atmosphere. The atmosphere can absorb the solar wind a little bit. That's where, the northern lights come from, is when the atmosphere is getting bombarded by the solar wind before it reaches the ground. And what about the stuff that gets through the atmosphere? Or the things that we own that are above the atmosphere? We can encase satellites in a thicker metal. We can encase their electronic devices in a thick metal to protect them. If we know that the space weather is coming, if we can forecast it, there's some things we can do too. We can plan for gaps in radio communication. We can course correct our satellites because the space weather can affect the trajectory of satellites, and if we course correct them, we might be able to have them avoid space junk. We can unplug our power grid so that it doesn't fry all the transformers. And we can prepare for not having power, prepare for power outages by storing food and the like. So how well can we forecast space weather? In short, at this time we can't forecast it as well as terrestrial weather. But if you go on this website, swpc.noaa.gov, you'll see our best forecasts of the space weather to this day. And you can see the speed of the solar wind. Now it's only 415 kilometers per second. The 750 kilometers per second was the fastest solar winds. You can see the solar wind's magnetic field strengths and the transverse and the z direction measured in nanotesla. You can see the radio flux measured in solar flux units. Well, these letters and numbers, G1, G2, I'll explain now. So there's 3 types of space weather that are forecasted on this website. Geomagnetic storms, solar radiation storms, and radio blackouts, G, S, and R. So on these days, February 3rd, 2022, there is G1 forecasted, a G1 storm, and on February 2nd, there's a forecasted G2 storm. So G2 is a worse storm than G1. The bigger the number, the more extreme the space weather. What are the differences between the letters G, S, and R? So a geomagnetic storm for G is a disturbance in the geomagnetic field caused by gusts in the solar wind that blows by Earth. So that's having to do with particles. Solar radiation storms are elevated levels of radiation, light, that occur when numbers of energetic particles increase. And R are radio blackouts, disturbances of the ionosphere caused by X-ray emissions from the sun. So remember, the ionosphere was that layer of the atmosphere that radio waves need to be able to reflect off of in order to be able to go very far. So that's about how well we can forecast it. What is being done to research it here at NJIT? You may have heard of the Institute of Space Weather Sciences, or ISWS. If you haven't, you can learn more about it at their website. NJIT has an NSF grant called Machine Learning Enhanced Cyber Infrastructure for Understanding and Predicting the Onset of Solar Eruptions. So the idea is to use machine learning to predict solar eruptions, how they begin. There's widely published research at NJIT, 11 publications in 2021, 55 publications in 2020. And there's lots of students. There's 19 graduate students, including me, and there's 5 undergraduate students involved in our research. So thank you for listening to my talk, and let me know if you have any questions. Thank you.